afternoon. It's 5 p.m. and thank you for those that they come on time. Thank you. And I'm going to start. Still, I have to hear from 5 more students, but hopefully they can just attend to this class as soon as they can. So today I sent another email. That's the 4th email. It's not to everybody, just for those that they didn't answer to that question. Do you want to come to the face-to-face lab? And 2 of those actually answered me today. Thank you. But it's still about 5 or 6 students. I need to hear from those. So please answer me. Do you want to come on to face-to-face class for the lab or not? I wanted to hear you here to the end of this actually week maximum, because I have to report that to the school and I have to know. Please do it as soon as you can. So another thing that is important, I want to actually make sure that when you are attended in this class, I want to make sure if you are in the class or just I can see your name here and you went to somewhere else. It happened before. I checked and I asked somebody and no answer for about 20 minutes. So please, if you are in the class, I want to make sure that you are in the class. Just I'm answering one of the chat. Please let me read that. Yes, I know that you added a class just recently, so you can go online and see the lectures, read those by yourself. If you have any question, you can come to the lab hours. That's you can be at the end and ask me any question you have, and please just do it fast, because you have to learn those stuff to be able to understand what we are talking about on the other lectures. So please, I ask for 2 things. Answer me today if you want to be in the face-to-face lab or not. If you don't want, there is no consequence for that. Just let me know. Yeah, and that's very hard for me to understand when you get the email while you are not answering. That's a negative point to my mind, and that's not good to actually you make some negative point in any other people. They can't trust you that much. Yeah, as soon as you see something, answer that. It's not that it's not a big deal. It's very easy to do. If you're not doing that easy stuff, if we ask hard stuff, are you going to do that? So please do it today, and after today I'm not going to accept the results. Just today is your last day to let me know if you want to come to the face-to-face lab or not. Otherwise I'm going to report that who answered, who didn't answer. Okay, so, and the second one was, I want to make sure that you are in the class. I will put note in front of your name whenever I check and you are not in the class. Your name is here. I'm not talking about just maybe 1 or 2. I'm not talking about the rest of the class. I love everybody and I like to see you are in the class. If you have to do something more important, do not come to the class and let me know. Yeah, I'm your friend. I'm not your enemy. Just whatever you want to do, let me know. I will help you. But if you are doing something behind my back, I'm not going to help you. Understand? Please do something to make my trust. That's the word that if we cannot trust each other, we cannot do anything. Yeah? Trust is the highest valuable thing that we can make. And if you make it, don't destroy it. Yeah? Okay. So I'm going to continue with the theme, and for the homework, maybe 1/3 of the class or a little more, they send me the answer. Thank you for those, and I respond some of those that I saw some problem, and I ask some of the students to talk to me at the lab hour. I want to ask them about the solution that they made, and those are important. And if you are not solving the examples, and just email me, just email me the answer. That's it. I don't want you to put in somewhere. Just take pictures, send that to me by email.
Are we going over the homework, and do we receive points for the homework?
There is no point for the homework, but if you have any problem, all the office hours is for you. At the end of the lab hour, I will be available and I will answer all your questions. Yeah, the homework are exactly the same as the examples that we solved. So if you still have problem, and I'm giving those to make sure if you can solve them or not. You can find your problem and find them and then answer the question, and I will review that with you guys in the lab hours. So those are for those that they want to spend time to solve the problems, and I will actually in front of your name to see who did that, who actually doesn't actually solve the problem, and the solving the problem will help you to actually just do better in exam. Okay, one of a student raised hand. Yes, what's your question?
So since we're not turning it in, so if we do decide to do the homeworks, and if we just have any questions, we could just email you the question and then our word just to see what we did wrong, and then you could just help us out from there.
No, I want everybody to send the homework to me. That's my point. I want you, please send that to me. But if you cannot solve them, go to whatever you can solve, and then the rest, you have problem. That's the meaning of a homework. I want you to make sure that you have problem or not. Send the answer to me, and if you have problem, come to the lab hour at the end. I will answer all your questions.
Do you want us to email you the homework every time it's due?
Sure. That's correct. Yes, please email me your homework answers and ask me the question if you have. Let me read your actually chat. Should we wait for our scheduled lab to go over homework, or can we show up to any lab? Any lab. Yeah, any lab that we have, you can come at the end of the lab. That's your time to ask your question. And another question, can you post solution no, I'm not going to post solution. It should be like the answer to the homework. Yeah, I want to see who is going to solve those, and then if you have problem, you ask me. Yeah, that's your responsibility. I want to give some responsibility to you guys.
Can't you post the solution after we turned it in, after the due date, so that way cheating is inevitable and we have the benefit of looking and comparing our work?
Look at this. No, because as my experience, not all the students are going to submit the homework, because it's not. It has no point. Yeah, some of the students, they are not sending any, and I don't want them to have the solution. No, if you have question, please come to the class. You know that what's your problem. I want that. Solution of those homework is exactly the solution of the examples. Could examples solve your problem? No, because you still have problem with the homework. If I give you those and I ask you to solve another homework, you need a solution for that homework as well. Do you know what I mean? No, you have to work on your knowledge to be able to solve the problem. That's my point. And please accept that. I know what I am doing. If you do this, you will learn better. If I give you all the answer to the homework in the book, you cannot learn that well. Yes.
If we got pretty stuck on all of them, is it feasible for you to go over all the homeworks in the lab hours?
Look at this. If you stuck to all the homework, it means that you are not listening to the lectures and you didn't solve the examples. No, in that case, I'm not giving you any help. You must read all the homework examples. You must solve all the examples by yourself. Then go to the homework. If you start with the homework, you cannot solve them. Yeah?
I feel like I paid pretty good attention in the last lecture, and I had a good grip of everything and followed the examples. But I felt like the homework was pretty difficult compared to the lecture, and like a lot of things were kind of new in the homework that weren't on the examples. So maybe I don't know. If
Yeah, I feel the same way. It's like the terminology, since the examples didn't have a question to it, it was hard to relate this question to the examples and just knowing what everything meant in the question.
Okay, so I agree with you guys. I'm agree with you guys on the actually the format that they use in writing the question. That's correct. It has something that is not that easy to understand. I can understand that. Try your best. Look at this. I am your friend. I don't want to push you to some way that you cannot learn. I want to push you to the way that you can learn better. Please understand what I am doing and what I am taught. If some part of that you cannot understand, yes, please come to the class. I will go through that, the meaning of those parts, but not to at the due date. You know, you can start that with the 2 days before due date. Not at the due date, come to me and say me, okay, I can't solve the problem. That's too late. Yeah, 2 days before the due date, send an email. Then maybe if I can write that the answer, or I can set one Zoom meeting just with anybody that has problem. We can talk about that during the 2 days before the due date. Do you know what I mean? So do this. I will answer that. I will help you. Then you will be able to solve it by yourself. That's my point. Okay, I'm not going to answer this anymore because we lost 12 minutes so far, and I have to review a lot of stuff. For the homework, if you have question, lab hours, please, because we have to cover a lot of other stuff, please. Okay, so look at this example. This example.
How, if I did all the homework, how am I supposed to know if I did them right? Because I could fill out 3 pages of work and still get all the work wrong.
Look at this. Did you have any question when you solved the example, that homework or not?
I did, and I asked you, and you gave me some answers, but I had questions on almost everything.
Okay, so it means that are you able to solve all the examples by yourself? Close the example answer and solve it by yourself. Can you do that?
I could write stuff on the paper, but I don't know if it's correct because I have nothing to compare.
No. My question, if you start solving the examples that you have the solution, but close it and solve it by yourself, can you do that? My point, if the answer is no, it means that you are not ready for the homework. Solve the examples by yourself 10 times to make sure that you can do it without looking at the answer. Then go after the solution, solving the problems, homework. Do you know what I mean? That's my point. First, work on the examples, solve them by yourself. If it takes 1 day, 2 days, go after it. Then go solve the homework. Otherwise, if you cannot solve the homework and you cannot solve the examples, it means that you didn't study that well. You must be prepared yourself first, then go after example, those homework. Okay. This one is a beam that we know everything. Yeah, we know the size of the beam, and this is for some beam that exists. We know V, we know H, and we are asking for AS. Yeah, okay. We know F prime C, we know Fy, and we know the moment. Just remember, sometimes in the book they actually wrote something that is hard to understand. If the self-weight of the beam is included or you have to add it, don't worry that much about that section. Why? Because in future, you as a designer, you know what you are doing. Yeah, you know if you add the weight of the beam or not. So it's not a big deal. Right now is a little big deal because it's just started. So you don't know what should you do. So I'm going to help with those actually the meaning of those parts. So in this class, I will give you the weight of the beam, or I will let you know the self-weight is included. It means that you don't need to add that. Okay, so in this case, MU, it means that everything is included. Otherwise, we should write somewhere that weight of the beam is not included. And that's a factor moment, because it's MU, it's not just M. So it has 1.2, 1.6, it has all those factors. The only thing that we want to find is AS. How can we find that? I gave you two equations in the second class. One of them was based on the percentage of the rebar. Another, when you don't know the percentage and you want to calculate AS. One chat. Yes, all the examples are in the book, but I solved them in the direction that you can learn better. Yeah, if you go to the book, sometimes you can see a little bit of difference of the solution, and it has harder to understand that in the book, because before the students had problem to understand that, and because of that I put them in my writing and on this slide. And please, if you follow this instruction, you will be able to solve any problem like this stuff. Yeah, with this information or like this information. Okay, so in this case, we have to go after that solution that find A based on all other information. And as I mentioned, MU and everything here go with a pound and inch. Just remember, use the same unit. It's actually, you can use it in this equation. In this case, I used pound inch, PSI, inch square, everything based on pound and inch. So the answer at the end should be inches. So, okay, so it was 2150, actually keep inch. So I will multiply by 1000 to convert that to the pound inch. Okay, then use it here. D is h minus 2.5. How we can get this? You can see 2 and h. H minus this will give us d or dt. At this case, both of them are the same. We have one layer. We have one layer rebar. Put that in this equation, everything, and because we need phi, remember always, right now we cannot calculate phi because phi has to do with C. We don't have A, we cannot have C. So we have to assume phi. So because of that, I'm asking, close this example, solve it by yourself. If you can solve it, you can solve any problem like this. If you cannot solve this, you cannot solve any problem like this. Yeah? Start with the examples. Through the week, through night. Do it, and then go after the homework. Then you can see you can solve them much better and faster. So, in this case, you can calculate A. Then,
can you remind us what A is, what that measurement is?
A is the depth of the compression in the concrete, that block, that rectangular compression block on the concrete. A is the depth of that. Yeah, so that's A. Then find AS. AS from this equation, I gave you A and AS on that slide, and I asked you to write them down on the paper. I'm not sure if you did that or not. If you did right now, you can look at those. Yeah. Then AS, this is the equation. You have everything. Put this in this equation. AS is 3.48. And we will go to the table. We are using 2 number 10 plus 1 number 9. Total AS of this from the table is 3.54. Is greater than this or equal, that's good. So it's greater than this. We accept this. Then I will go after beta 1 because I want to find C to check phi. Because
Professor?
I assume. Yes.
How do we know that 2 number 10 plus 1 number 9?
Look at this. You have to find some number of the rebar. Don't actually work on this part right now because you have to have experience. you have to pick size of the rebar to be able to reach to this. If you go with 10 number 3, you cannot set those. You know, with too much rebar, and you have to have a space based on the spacing that I gave you. Then you can see you can't do that. So you need some experience on this one. Don't worry about this. And at the end of this class, you will learn a lot. And then when you start working, you will learn more. In this class, I will give you the number of the rebar that you can set. You know, you need more experience just in the work. Don't worry about that part. But as you can see, I picked something that must be close to each other. I cannot go with 2 number 10 and 1 number 3. That's wrong. Yeah, must be close to each other. Number 10, number 9. Number 10 and number 3 is not a good match. Do not use something like that. So I will go with 2 number 10, 1 number 9. It's 3.54. It's close to this. That's good. Yeah, so I picked this. So you will learn. Then go after beta 1. That's the beta 1. Beta 1.8. And then C is equal, what's C? Neutral axis. A divided by beta 1. 6.13. Yeah. With this phi, I will go after C to check it. How can I do that? I will go with the second equation of the phi. We had one C over dt, another based on epsilon t. What's epsilon t? Means tension bar, means epsilon s on the slide on the second actually class. That's the equation for that. We know D, 13.5. We know C, we calculated. Put this here. Then put this in equation for the phi based on epsilon t. Based on this, you can find 0.78 is between these two. You are good. So let me answer what chat.
Epsilon u will always equal 0.003.
Yes, always. What is beta 1? You know, in my notes I wrote that it was related to the factor of safety, but I don't think that's correct. Look at this. This beta 1. Those are parameters that they can convert something to something else. Those are the parameters that we can convert that curve for the C to the A. That's the height of the block. So if you change that beta 1, you can change the A. So it has something to do with the total factor of safety of the reinforced concrete design based on the ACI. That's correct. Yeah, that's correct. But that's the factor that can convert the location of the C to the A. And it's not perfect. It's not exact. But that's based on the code. They came out with this equation. And based on this, you can calculate C. So, after this, you find phi. We assumed that phi 0.9, but we got that 0.78. That's not correct. So we have to redo this. When phi is decreased, for our assumption, we must recalculate the beam moment capacity. So as soon as we got this, it means that it wasn't correct. You can do something. You can go with phi 0.78, go to this equation, recalculate A, then do this stuff and find phi, and find, based on this phi, if it's not the same as what you can assume, go to this again, find A, and redo this until these two phi, after few try, are very close. But you do not need to do that. Yeah. When phi is not the same as that phi, you can go and redo everything until you get the same phi. It will take maybe 3, 4, 5 tries. You don't need to do that. Just instead, you can go and find the moment capacity based on this phi, not that phi we calculated. Do you know what I mean? So you can go either way. But based on that code, we do not to go to do that 5 or 6 times try. We don't need to do that. The difference should be minimum, and there is no need for that solution. So, how can I find the moment capacity? I know AS because 3.48. I know D, 13.5. I calculated A, this one. So, what should I do? Use this equation and find the moment capacity, and everything here is 60 KSI, in inches. So at the end, I will get inch cube. That's the MN. Yes, Chris, what's the question?
I was a little confused on how we got 13.5 inches for D because we don't know H, right?
H 16. Look at this.
Oh, sorry. I need to get
Yeah,
oh, thank you.
You're welcome.
Professor?
Yes.
So from what I gather, it's like, so we do the first few calculations, and if our phi doesn't match our assumption, then we can just simply use the MN formula and then calculate from there.
That's correct. But if you are curious that can you do this or not, if you go and recalculate A based on this phi, and then at the end you will get 0.78, you will get 0.81. Then use 0.81 here, then you will get 0.79. Then use that one. Then after a few times, those two will be close to each other. Then you can accept that. And then when you calculate that, at the end, the answer, the difference here should be minimum. Instead of 1898, you will get 1902. You know what I mean? So
Yeah.
there is no need to go and to do that. As soon as you calculate this phi, you can go and find the moment capacity, and mu capacity means provided moment, ultimate moment is phi times mn. That's your max ultimate moment capacity, 1898 inch cube. But we wanted 2150. After all this work, at the end we got that wrong. Yeah, it's not acceptable because the moment capacity is less than required. This is mu from loading is required. So two number 10, 1 number 9 is not a good deal, is not acceptable. So what should we do? We have to go after another try. Another try in the if you are doing that, if you are not that expert, you have to do this times. At least you will go with three number 11. Then you can see that's a huge actually difference. It's too strong. Then you can change it. But in this class, I will give you the rebar whenever it's needed, yeah. And I will ask you to check the capacity because I want to make sure if you know the size of the rebar, can you find the capacity? This is important. Later you will learn that combination of the rebar in the real design. Let me answer one chat. Do we need to be using tables during solving examples? No, there is no need except that AS, yes. And you can see I put that in one that slide on the second slide. I think I put that here too. I'm not sure I will. You can see have that table always with you. Yeah, you don't need to remember something. You can pick that number from that one. So. So do we need to assume, look at this, yes, look at you ask the question from top. This phi, because there is no C, you have to assume phi. You can assume any number, but 0.9 is the easiest. It's up to you, yeah, that's up. If it's not at the end, if it's not the same number that you assume, you have to redo this again, yeah. So 0.9 is the easiest one. So, in this case, because it's not good, we will change that to 3 number 10 instead of 2 number 10, 110. So what should I do? 3 total AS is 3.81. Redo everything again, yeah? But because I know AS, I don't need to calculate A because from this equation, yeah? Because I know AS at this time. At that time, we didn't know AS. We want to calculate. Yeah, so in this case, just I distracted with that one student wanted to attend. I was here because we have AS, so we can use this small equation rather than the big equation. Over there we had no AS. Here we know AS. So put this in this equation, find A, then beta 1 will not be changed. Why beta 1 is not changing? Because beta 1 has to do with f prime c. So whatever it was, you can use it here. So that's your c. What's c? Location of the neutral axis. What's epsilon t? Based on the equation, find based on all this stuff. Redo everything the same as what we did above, yeah? And calculate phi. So phi is 0.836, and we didn't assume anything for phi because we had AC. So based on that, we can calculate phi. This is the real phi, okay? Mn ASFI, and then that's the moment capacity provided based on the material. Mu capacity provided by material, phi times Mn. And as you can see, this one is greater than or equal. If it's equal, it's acceptable. A little bit even less. If you get 2149, it should be acceptable. Do you know what I mean? So the difference, you have a lot of factor of safety. None of those factor of safety are at the wrong direction of the factor safety factor. So all of them will add to our factor of safety. So at the end, if you go a little bit behind that, in real design, we accept that. You know, in this class, it's up to you. If you don't want to accept, if it's not greater than that, you can say not good. If it's equal or greater, then it's okay. So then we have to check the reward. Minimum required reward, maximum of these two. We did that a lot last time. So that's your rho max, rho mean, chat. Beta 1, look at this. That's the equation for beta 1. Question is how you can calculate beta 1. Look at this. I like you guys to ask question, but your question means that you are not actually review this stuff. Please, that's the third week of this semester. Yeah, please solve all these examples by yourself. If you wanna pass this class, if you wanna get a good grade, listen to me. I'm your friend. Yeah, if you get good knowledge, I can proud of you guys. I can say, hey, you look at these guys, they were very good students and right now they are doing perfect. This is the equation for beta 1. Please do your work. Yeah, after this, read those stuff. Okay, what's the question?
Since phi equals 0.836 in the second calculation, do we have to do it again since it doesn't equal 0.9?
No. Look at this. For this second one, forget about the top part because it was wrong. Yeah, this moment capacity was less than this. Not good. So that's it. This is the second part. So in this part, we didn't use phi. Look at this. We used that phi in this equation. We need that. Because of that, we assumed. Over here, because we know AS, we are using this equation for A, and there is no phi. So we didn't assume anything for phi. That part, forget about that part, because it wasn't good, not good. So this part is not acceptable. This is the second part we started. And in this case, we know AS because we used tree number 10, and there is no phi involved. So we didn't assume any phi. It was a good question, yeah? So in this case, there is no phi assumed. This is the real phi that we calculated based on A and C that we have. Over there, we have to calculate A based on the phi. So we have to assume for phi. This A has nothing to do with phi. So there is no need to assume any phi. Good question. Okay, so at the end, rho mean, we picked that maximum of these two numbers. What's the rho max? That's the equation for rho max. You know that. So put F prime C Fy here, you will get 0.024. And what's your rho, percentage of the reward? AS divided by BD. AS 3.81, B 12 inch, and D 13.5, 0.235. As you can see, this one is less than this, less than 2 rho max, and this one is greater than rho mean, so we are good. Let me read a chat. So, chat. Yes, AS tree number 10. The question is, are you finding the AS from the chart? Not the chart, that table. Tree number 10. 3 number 10, you go to that table, each number 10 is 1.28 times 3, you will get 3.81.
Oh
Yeah,
my God.
there is no chart. That's just tables that I gave you. Any question?
In the book, they use row 005. Is that same as
So,
row 005?
look at it. You can go with 0.005. That's the meaning of my actually thing. The book is kind of research kind of solution. You don't need to go after that. I gave you everything that you need to use in the work, real work outside. And then if you want to add to your knowledge, you can go after something else. Then you can go after some research. These are based on the code. Your row must be between row mean and row max. If you go with row 0.005, it's acceptable because you got 0.005 that will give you a smaller row. You know what I mean? That is less than row max. If you increase this number to 0.005, you will get a smaller row. So it's less than row max. It should be acceptable. But I don't want to confuse you. Yeah. So please just listen and follow this instruction. When you got this completely, then if you go after that, you can understand what's the difference. But right now, it can confuse you. Why row 0.005? No. 0.005 is less than this, so it should be acceptable. But based on the code, you must be between row mean and row max. Yeah? So
There's just in the examples that you had assigned to us the sample questions. So
okay. Okay, so did you get it?
thank you.
Perfect. Very good.
For the first half of this, since phi equaled 0.78 in the first one, we don't have to recalculate it since we know the moment's going to be smaller than required. So we just
That's correct. Look at it. So there is no need. It is wrong. Yeah? So there is no need to do this. And that's part of the knowledge that you will learn later. If you go after that, try, or no. Check it. If it's not good, stop it. Go after new solution. Yeah? You will learn this stuff. And in this class, because I know you have to learn something, I will give you something and I will ask you to check it. Do you know what I mean? I want to see if you can follow all the information based on the code. This is the thing that you must learn in this class. Then for the research, in master degree, we will give you something that is not exactly in the book or in the ACI. Then you have to do a lot of search. But here, just I want to make sure that you can follow the code perfectly. Okay, so let's go after another example. This example, I have a beam that we don't know we have nothing, but we know mu. It means that self-weight is included. Yeah, self-weight is included. So how can we start? Hopefully you review this the lecture and all the examples by yourself, because I solved one example almost close to this last week. But the first thing that you know, find beta because Ephraim C, that's your beta one. Then epsilon, you know this, actually epsilon you can find row max and row mean. Yeah, so that's whenever you have three unknown. I gave you example last week. You have to pick something to be able to solve it. Otherwise, you cannot. You have three unknown here. Yeah, you know AS, you don't know AS, you know B, you know B, you don't know H. So how can we solve? At first, we will go with something. Okay, we will go with 60% of row max. This is the good guess always. Yeah, I put just this for your information. If in future you have something like that and you don't know, you got your BS degree, yeah, and you are going to solve that example, how to start? That's a good guess always. 60% of your row max. It's a good start. Okay, so I started with this. We assume this row max, 60% of that, it means that the percentage of the rebar is 40% less than row max. So we are good, we are safe. So that's row. Then I gave you the second moment capacity last week. for provided moment. That's the second equation based on the percentage of the rebound. Okay, and I know that phi times mn will give us mu provided. So mu provided, phi mn. Okay, and in this case, I'm going with something like this. If mu provided is equal to mu required, mu provided is equal to mu provided. Just I want to start, yeah, because I want to be at least equal to moment provided, moment required, ultimate moment required. So I put
the computer cut out.
Okay, so look at this. I know that the moment capacity based on the material, and phi times mn will give us ultimate moment capacity based on the material. And I know that the ultimate moment capacity from material must be at least equal to ultimate moment capacity by loading, at least, or greater. Okay, at this time, I will go if the moment capacity by material is equal to the ultimate moment by the loading. Yeah, I will consider these two sides equal. And this Em is phi, look at this phi, yeah, and how can I calculate phi? I don't know C, I can't do anything for phi, and because of that, you can see we have to assume it. Why? Because we don't have C, we have nothing, we don't know BH, so we have to assume, yeah. So right now you can see with all these examples, you can see when we need to assume something, yeah. There is no way to calculate that, so we assume 0.9 times rho, your rho is 0.00. I put everything here. B, I don't have that. D, I don't have that. BD square, I don't know. Times all this stuff, we know all this. Then solve this and calculate BD square. That's a BD square. This much we need that. This is required. Or if you go with higher, is better. Because we assume that the moment capacity is equal to the moment loading. If we use bigger size, so moment capacity is more than moment required, so we are good. So that's the minimum required. Okay, so still we have two unknown. What can I do? Assume one, calculate that, and then check. Okay, so we assume B is equal 10, and then put this in this equation. D squared should be 280. D is equal to 16.7. That's not a good number. We are round it up. How you can do it later you will learn. But I put something that you know that most of the time we will go with something that 5, 10, 15, 20, something like that, or 1.5 foot, something like that. 31 inches sometimes maybe is not that good, but it's not that bad either. If you want to go with 31, the inspector should check those numbers. Do you know what I mean? It's not prohibited by anything, by code that you cannot use. No. You can use it. So you can use this, just it's better to go with something that is wrong. That's up to you guys. But here we use, instead of 16.7, we use 17.5, and we increase the moment capacity. Okay. Then what should I do? In this case, right now, I want to find the AS based D that we calculated. So we know B 10, we know D 17.5, but we don't have AS, and we know the moment. That's the moment caused by the loading. So what can I do? The same as the first problem. Look at this. The first homework, this problem, we have BH means D and everything, and we have the load. We started with A, yeah? So we are going to do the same here because we want to find AS, and we know B, and we know D, and then how to calculate this? That's A. So we go with A, and still phi, we assume that C is 0.9, yeah? Because we can't calculate that. We don't have C to check phi, so we assume phi. We use all these numbers in this equation, find A, and then AS, and then for AS 1.96, we will go to that table. For 2 number 9, you can see each one is 1 square inches. So 2 of them will give us 2 square inches, very close to this. That's good. Yeah. So I put a note here for you guys why we cannot calculate AS from row BD with that row. That row, we assume that, and then we change D. So that percentage is not acceptable here. We cannot use this. Yeah, just a put side note for you if you think why we are not doing that. That's the answer. So we pick 2 number 9. That's your AS.
I got a question, Professor.
Sure.
So with the row, why did you use 0.0124 instead of what you calculated? Because you calculated row max as 0.0206, right?
Yeah, but are you talking about this equation, why we are using 0.0124?
Yeah.
Yeah, look at this, because I told you it's better not to use row max. We are using 60% of row max. This is our actually usage. Yeah, we are using 60% of the row max for our row.
Is that always?
No, that's a good guess. Look at this, it's not always. You can go all the way to close to row max. Yeah, it's better not to get that close because you will get a problem with the concrete in comparison, as I mentioned before. But the code is not stopping you. If you want to go with very close to this, go with, instead of this, 0.2. It's acceptable. Go 0.201. It's acceptable. It's less than row max. You know what I mean? But for a start, this is a good guess. You can go with this just as some tips. Yeah, that's a tip that you can see. It's a good guess for a start solving the problem. And as you can see, we changed that. We are not following that. This is just a start to find B and D. Then we will go with our assumption. Yeah, we will go after the real rebar. We didn't use that number here. We calculated A and AS. Okay, so we picked 2 number 9. That means AS2. Did I give you the answer?
Yeah.
Okay. So then, because I assumed 0.94 phi, we have to check it. Right now, I have C because I calculated A. A divided by beta 1. Beta 1 was 0.85. So we calculate this. Then D is equal DT because DT for one layer and layer D and DT are equal. So D is equal DT 17.5. Then at this time, I went with the other equation for phi just to practice. The first example with epsilon T or epsilon S, here C over DT. Yeah, you know C, you know DT. Put this in this equation, you can calculate phi is equal 1.3, but it must be less than or equal 0.9. So phi should be equal. So that assumption for phi for 0.9 was acceptable. Yeah, if it wasn't acceptable, with this new phi, go to this equation again, find AC and check your phi. If it wasn't acceptable, go to this and redo it to, at the end, you will get very close. That's your final. Yeah, so that's the actually circle that you have to go, do it to at the end get the same phi. Yes, what's the question?
If phi ended up being 2 or 3, would that still be acceptable? Can we still just set it equal to 0.9 and say it was okay?
That's right. If you get even 10, doesn't matter. It shouldn't be greater than 0.9. You should consider that 0.9. Clear?
Okay.
Professor,
yes.
how do you, kind of similar to that question, what would be considered unacceptable then? Would it have to be something, you said if it's really large, if it's 10, it's fine, just use 0.9.
No,
what about if it's like 0.65, under 0.65, is that unacceptable?
Not important. No, not important. Just calculate your phi. If there is no limit here that phi should be less than a number. No, just when you are going to use this phi, your phi must be less than or equal 0.9. That's it. Forget about what you can calculate. If it's 10 point something, don't think about that. Do not use phi greater than 0.9. Yeah, and why? Because look at this: mn is equal mu is equal phi mn. If you use phi more than 0.9, if you use, for example, 6.3, it means that the moment capacity ultimate is greater than nominal moment, and the ACL doesn't like that. Yeah, the code is stop us. We want factor of safety, not reducing the factor of safety. If you go with phi larger than 1, it means that we reduce factor of safety. Is that clear?
That part makes sense, but I guess a follow-up question would be, so, you were describing sort of that iterative process of, if you have to recalculate phi, what would be an example? How would we know that it's not acceptable and we need to go through that iterative process to recalculate phi? Or you're saying we just don't do that?
Yeah, there is no need to do that. There is no, actually, I'm not sure if I understand your...
It's because on the last example you wanted us to go through the iteration because we got 0.78, and you said we would have to redo the calculations, but in this scenario we don't for some reason.
Well, so, yeah, that's kind
No.
Next,
No, let me see. Look at this. No. Look at this. Because your phi was 0.78, but we assume 0.9. Because of that, you have to go after this. If you calculate this phi here and you got 1.6, you don't need to, should be less than 0.9. So you have to go with phi equal 0.9, and because phi 0.9 and phi you assume 0.9, it was good. But when it's less than that, you have to go and redo this. Is that clear?
Okay, so when we get something in the middle of those two, we have to go through the iterations?
That's correct. If this one is not equal to this, or far from that, yeah, so you have to go after this one. But in this case, we assume 0.9 and we calculate that 0.9, so there is no need to redo this again. Forget about 1.3. Based on the code, this number can be anything, but at the end it should be less than or equal 0.9, greater than or equal 0.65. We calculate at 1.3 based on the code. You must consider that 0.9. That's it. And this 0.9 is the same as this, so there is no need to recalculate anything. But the other example, we calculate that phi and we ended up with it, and it's between 0.9 and 65, and we have to accept this. But we assume 0.9, so it's not acceptable because we assume 0.9, we got 0.78, so we have to redo this. In this example, we assume 0.9 and we calculated 0.9. Is that clear?
Yes.
Everybody?
not entirely, but
Yes.
I don't know if I'm going to get it.
So, yes.
So if it's under 0.9, then we have to redo it. If it's over 0.9, we don't have to redo it.
Look at this. Please listen to me. Whenever you calculate something above 0.9, it's not acceptable. You have to consider that fee less than or equal 0.9. So if you calculate this and you get 10.8, you cannot go with 10.8 because code gave us the limit. You must consider that less than or equal 0.9. If you got 10.3, you go with C equal 0.9. That's it. So, this is your final answer for phi. This final answer is equal to what you assume, you are good. If it's not equal, go through redoing all those stuff. Is that clear?
Yes.
So, if you still have question at the end of the lab, please, I will go through this few times to make sure that you got it.
And then what if we got something, if we estimated or assumed 0.9 and we got something less than 6.5, do we keep that number? Do we
Look at
go
this.
to
If
65?
it's less than 0.65, look at, you have to go with 0.65. You have
Would it
two
have
limits.
like 2 iterations? We just stick with 0.65.
No, you have to go with phi 0.65, but because you assume 0.9, but you got 0.65, you have to go through this again and again. Because you assume 0.9, but you got 0.65, so you have to do it.
Okay. Alright.
Clear? Okay, so how can we find, check the rebar? We have two number 9, so go through this equation, yeah, minimum and max, and you can see with this one, AS means 2 square inch divided by D divided by D 17.5. It's between rho max and rho mean. We are okay. That's it. As you can see, it's very clear, actually, solution for all these beam like that. And then I'm going to start this rectangular beam with tension and compression rebar. So please, more attention to this. This is a little harder than that tension bar only. Okay. We have to do something to ensure if we need compression bar on top or not, and you need this for the lab as well. Please read this. I think today after class, review this, solve the examples by yourself. It can help you a lot. So at first we have to design the tension bar, like a regular, like the chapter that we went through so far. Then find the percentage of the rebar. If you have a T shape, I shape, whatever, look at this. The percentage of the rebar, pay attention to this. You have to read a lot of book and other stuff. Just with this small graph, you can see the meaning of the percentage of the rebar in the beam. If you have any shape rebar, for this one you go with BW times D. BW times D. Forget about the other flanges that you can see. If you have rectangular section, D is equal BW, because you don't have flange, you have just web. But whenever you have web and flange, we call this flange, yeah, and web. So this rectangular section has just web, there is no flange, so B is equal BW. So this is your main equation for tension bar. We need that. Please draw something on that paper to make sure that you can use the right numbers for finding rho. Then, if your rho is greater than rho max, then one of the solution is adding compression bar on top. Yeah, or you can change the size of the beam. Sometimes you can't do that. The architect will stop us, give us the limit for B and H. So in that case, one of the way is using compression bar on top, or using better tension bar with a higher Fy if we can. Sometimes we cannot. So in that case, if we have compression bar, look at this. Compression bar is for simply support. Compression is on top, tension at the bottom. For cantilever, that you have tension on top, you have tension bar on top, compression at the bottom. Just you have to turn this 90 degree. Yeah, 90 degree, turn this, so you will get those rebar at the bottom, this rebar on top. It means that for negative moment. We went through this last class. Yeah, review those stuff one more time. So in this case, all the rebar in compression and anything has to do with the compression, we will use with prime. So A prime S means compression total cross-sectional area of the compression bar. Do not look at one. Just it means that the total amount. It's not just one compression. We are not using one on top, minimum Q for the beam. So AS is total cross-sectional area of the tension rebar. And this is a strain diagram. A strain diagram will pass through the neutral axis. Yeah, this is the neutral axis. Perfect. So this is the E prime S. Last class I gave you ES or ET. Right now, I'm giving you E prime S. Why? Because we have E prime S. Because we want to make sure that that steel in compression will reach to Fy or not. Okay, that's the equation. You need this equation. Yeah, you need that. Then, in order to solve this, that's a complex problem. How can I solve this? I look at everything that we have here. We have concrete block. That's A that you asked in the start. This is your A. Yeah, the height of the compressive block in concrete. C, neutral axis. A prime S, F prime S. I don't know if the steel in compression will reach to Fy or not, and because of that, we call that F prime S. Stress in steel when it's in compression, F prime. But when we are using a system like this, for sure tension ball will reach to Fy. Yeah, because we have too much load, and because of that we have to add compression bar. So for sure tension will reach to Fy. So always Fy. That side we don't know. We have to check and find it. Okay. How can I find this stuff? I will split this to two parts. If you understand this page, you can solve all the examples that looks like very hard in this actually section. Please pay attention to just this small part. Okay, I will say in order to find the moment capacity of this, because these are the material, I will split this to two parts. Part of the AS is equal A prime S, F prime S. So I have two equal forces, always couple force. Can you remember? I call that C capital for concrete should be equal AS F Fy for that first section. Over here is still the same. So these two forces must be equal, different direction. So I know I have steel with this stress. A prime S times F prime S means this force, total force. How can I find F prime S? F prime S, E epsilon prime S. This is your epsilon, the strain in the compression rebar. So I can find F prime S based on this equation. These two must be equal. Okay, I will consider part of this as A prime S, F prime S. Yeah, so this part plus that concrete block. Yeah, because if I add them together, I should reach to this. And then for this one, remaining of the rebar. So AS Fy minus A prime S F prime S. This force minus this force mean the remaining of the force from steel in tension. So AS Fy minus A prime S F prime S should be this. I can rewrite that like this one. Yeah.
Now we have compression on the bottom of the beam as well?
No. Look at this. That good question. This is in tension, but because I want to show you how we can reach to the final equation, just I will say part of the tension rebar equal to this. It's not in compression. I will look at this. I show the tension, but with the same amount of as the compression bar. Very good question. So it's in compression, but opposite direction equal to that.
To keep it in equilibrium?
Perfect. Yeah. So how can I calculate the moment caused by this? Because those are a couple force. So one force times distance. How can I find the moment of this? This force must be equal to this. Yeah. So that force equal to this. One of those two times distance from center of this to this rebar will give us the moment capacity. So we'll have one moment capacity from this, one moment capacity from the other one. Add them together, that's your moment capacity. If you got this, you are perfect. Yeah? So, then I will come to this part. Again, I will show these two parts. This part is this. Yeah? So, in this case, A prime S, F prime S, tension, but A prime S, F prime S. Perfect. So, how can I find that A? Yeah, I want to find that A to be able to solve this problem. Okay, this A will come from here because I have to find this. Look at this. This rebar, this force must be equal to that force. Yes, what's the question?
Oh, never
What's
mind.
the
I was gonna. Where is D prime?
D prime, good question. From center of the compression rebar to top, look at this. That's your D prime. Yeah, center of compression bar to the top. That's the D prime. So, in order to find this, again, exactly the same as tension rebar, but over here, your tension rebar, the remaining of tension rebar is this one, is equivalent to the compression concrete. So that's the same equation, but with this ASFI. It was ASFI, this one is AS minus something times FI. The same 85 prime CB. You can calculate A. Then you can calculate C. Then you can calculate F prime S, because you can calculate epsilon prime S times ES. Look at it, epsilon prime S with C and D prime times ES. This one is the same as this, yeah? So we calculated F prime S. If F prime S, again, always this is our limit, greater than Fi, F prime S is equal to Fi, not more than that. If you get F prime S 70,000, like that phi, if it's more than that, you shouldn't go with that number. Always your limit is Fi. For that one, always your limit is 0.9. If you get whatever for phi, it should be between those two limits. Not less than 65, not more than 0.9. That's it. Over here, we are using the same, and we did that for other class as well. Your F prime S and Fs must be less than or equal Fi. If it was less than, accept it. If it's not less than, greater, go with Fi. Yeah, that's it. So how can I find Mn? One of these forces, because those are equal, times the distance. What's the distance? D is from top to the bottom. Yeah. Or if you have dt, actually no, d. If d is equal dt, you have one layer, doesn't matter. Those are equal. D equal dt. So d minus d prime. That's the distance. One of these forces, A prime S, F prime S, d minus d prime. So that's the first part of the moment capacity caused by the material. Then go after this one. We calculated A. We know A divided by 2 is the center of this reaction to the top. What's the distance between these two forces? Means D from here to top minus A over 2. Yeah. So Mn2 should be this force. What's this force? 0.85 times B times A. We did that on the first class. You have B times A if A is here, like this one. Look at it. A up to here. A times D area times 0.85 FRMC means the volume of that compressive block. Yeah, that's the volume. 0.85 FRMCBA. That's your force compression in concrete. So that force times this distance, or this force times that distance. Look at this, the distance is the same because those two are equal. 0.85 prime CAB is equal this force. Always, otherwise you cannot write this equation. Yeah, and final is equal Mn1 plus Mn2. That's your final. And most of the time, it's easier to go with this part Mn2 based on concrete, because you have to write a lot of F prime, find F prime C, but in that case, you don't need to do that. Yeah, most of the time you can see this equation. But if you write Mn2 instead of this part, if you use this one, it's acceptable, and you will get the same answer. Yeah, the same answer. So far so good.
How come for the second moment we don't have to use the neutral axis, the distance to the neutral axis C?
So look at this. Actually, we didn't use that neutral axis. Can you remember all the equations that we used? We didn't use. We used just A and D. Yeah, but A has to do with, because A is C times beta 1. So when you're talking about A, you're talking about C. Is that clear?
Okay.
Yeah.
Okay. So, what are the other steps? So far, we went through 3 steps. the fourth step is calculate tension rebar ratio, yeah, based on the final AS, yeah. So based on this, yeah, based on this, you can find the total AS. We solve example, you can see. Then calculate compressive ratio, rho prime, A prime S, BWD, BW web dimension divided by D. So if you have I shape or T shape, BW web dimension, width of the web. Rectangular, B is equal BW, that's the same. Then we have to calculate maximum tension bar when you have compression bar. You cannot use the rho max from the past. You cannot, you have to use the new rho max. What's your new rho max? The same rho max that we have, rho 0.004, that one. Rho max plus this one, rho prime, you can calculate rho prime, times F prime S, we calculate tension in the compression bar, divided by Fy, yeah? Then rho less than or equal rho max. If rho is less than rho max, you are good. If rho was greater than rho max, then stop and change F prime C, Fy or beam dimension. So it's not acceptable if you have compression bar, but your tension rebar percentage is more than new rho max, rho bar max, when you have compression bar. Yes, what's the question?
For the compression rebar ratio, should it be D prime in the denominator?
No. D prime is just the cover. D means the percentage inside the concrete. You know what I mean? So that's a good question. No, that's the percentage inside the whole concrete, not just the small cover part. No, it's D. Good question. Okay, let's go after. These are the rebar that I told you. I put that here, so just for you. And then right now I'm going to solve some examples. I have to cover a lot of stuff. We want to determine the moment capacity for a beam that you have everything. So it's based on the as-built. We know the size of the bar, we know everything, and we want to calculate the percentage of the rebar. We want to calculate the moment capacity of this beam. Okay, we know everything. Yeah, rebar, compression bar, that's A prime S. Look at this. 2 number 8, A prime S, from table times 0.79, that's the total area. 6 number 10. 6 number 10 means 6 times this, total cross-sectional area. Now I showed you DT, look at this, you have 2 layers, DT and D. D to the center, DT to the bottom. Yeah? And we consider 2.5 here, okay? And 24 to this side, yeah? You know DT and you know D. So DT is total H, 28, minus 2.5, D 24. And what's D prime? 2.5, yeah? This is your D prime. D prime, 2.5. So, let's start to see step by step that I gave you. I put that here. So if you follow that, you will not miss anything. So at first, calculate tension bar ratio. Rho, AS, D means BW, but because here is rectangular, B is equal BW times D. We have everything here, percentage of the rebar. Find beta 1. Yeah, that's your beta 1. Find rho max for 0.4. That's your rho max. Yeah, then you can see your rho, yeah, is greater than rho max. Your rho 0.0265 is greater than rho max. So compression bar is required. Maybe even with that one, rho is more than rho bar max. We have to check that as well. If it's more than that, the beam is not acceptable. As I actually mentioned that here. Look at this. In the last section, if rho was greater than rho U bar, but with compression, stop, your beam is not acceptable. You have to do something. Okay, so we check this and we notice that the rebar tension bar is more than we need. So what can we do? Then for this one, assume f prime s equal fi. You can go with any number like that c, yeah, but always it's better to go with fi. But if you like to just do the challenge, go and do it by yourself with something else to see how can you get the same answer. You have to get the same answer like this one if you go with any number. Okay, so but it can't be more than fi. Just remember, it cannot be more than fi. Fs or f prime s must be less than or equal. Okay, and that's the equation for A. These are the equations that you need to write on that paper. That's your A. Yeah, that's the equation. Put all these numbers, you have everything. You can find A. C divided by beta 1, that's your C. Perfect. Then go and see if f prime s is correct or not. Yeah. So this is the equation for epsilon prime times ES. ES is 29,000 or 30. I gave you here 29,000. Yeah. So 63.8 is not acceptable. It's more than Fi. So your f prime s is equal to Fi. Like that phi was greater than 0.9, you should go with 0.9. So in this case, we should go, and we assume that is equal to Fi. So we are good. If it was less than Fi, we should redo this again because we assumed Fi, but we calculate this instead of 63.8, we got 52.8. So we should use f prime s is equal to 52.8 because must be less than Fi, yeah, or equal. But if it's less, go with the less. If it's more, you should consider that equal Fi, the same as phi. Yeah, I'm repeating to make sure it will go inside you and you cannot forget this. Okay, then so far we are good. We are lucky. We assumed something and it was correct. Find rho prime. Rho prime is A prime s divided by B D. BWD here is D. So we have A prime s. We calculate this. Then find rho bar max, maximum tension bar in the beam with compression bar. What's rho max? This is the rho max for tension bar only. So we have that number from there. Plus this number. Yeah, put this here. This is your new, actually, look at this. Rho prime times f prime s divided by Fi. We got f prime s equal Fi. So times 60 divided by, I put all the numbers here. As you can see, this one is greater than rho we used. This rho, 0.025 This new rho bar max is greater than that. One of your friends just got in today, right now. So for the actually a new student that you actually got in very late, so you have to repeat this up by yourself. So distraction, I don't know where was I. So yeah. Now here, yeah. So our rho is less than rho max, so we are good. So the beam is acceptable, yeah, with compression bar, as you can see here. Then we have to calculate the moment capacity. How? First of all, we need phi. Why? Because we want to calculate M ultimate capacity. So we need that phi. So phi the equation, we have all those stuff. I'm not going to spend time on this. And over here, you will get phi is equal 0.95. Is that acceptable? No. Code ask us must be less than or equal. So phi is equal 0.9. The same as Fi. Yeah. It's what's more than Fi, we should go with Fi. More than 0.9, we should go with 0.9. What's Mn1 equation? That's the equation. We have all these stuff. F prime s, we calculated 60 is equal to Fi. Yeah, we calculated Fi. So put in this equation, add them together, that's your Mn, inch cube. We use KSI and inch, so it should be inch cube. Then phi times Mn will give us inch tip, ultimate moment capacity. So that's the ultimate moment capacity for the beam with compression bar. So is there any question on this one?
What is the actual answer that we were looking for?
No, nothing. Just we wanted to find the moment capacity. Yeah, but for example, in exam, I can give you check if this beam can carry ultimate capacity moment of 9,000 inch tip. So you have to do this, and at the end, you can see this one is less than 9,000. You can say no, it's not strong enough to carry that load. Is that clear?
Yes.
Perfect. So when you find the moment capacity, you are done. You can compare that with whatever you want. Okay, let's go another example. So in this example,
did the stirrups in that
yes.
last example, I didn't see them pop up in any of the calculations.
No, it's another chapter. We need one chapter for stirrups. It's another chapter. This is just bending moment, not for shear. Yeah, I will go through that in the next maybe 2 weeks. Okay, so we are going to actually determine the steel areas for the Shannon rectangular beam according to SCI code. Dead load, live load, simply supported 18 feet. So simply means tension at the bottom. Yeah, DH, we know everything. Yeah, and a stirrup number, I gave you a stirrup, you can see, because the number of the rebar that you are installing must be matched with the code, if you can install or not. So, in this case, we are going to determine the steel. Let's start with actually this system first. The weight of the beam is included because we didn't mention that consider the self-weight of the beam. No, so it's included. So omega u is 1.2, 1.6, and mu, because it's simply supported, omega L squared divided by 8. Yeah, that's for simply supported beam. So this one times L in the power 2 divided by 8, that 211 foot tip times 12 inch tip. Yeah, times 1,000 inch pound, but we start with tip. Yeah, inch tip, that's the moment. Okay, so at this time I want to actually check the see if the beam needs compression bar or not. So what should I do? At first I have to calculate, because I know the moment, I know B, H, F prime, C, F, Y, everything. So it's exactly the same as first example that I solved today. So, and I have to calculate A. In order to calculate A, I need C. Yes, what's the question?
So when we're calculating maximum moment, are we always going to do 1.2 times the dead load plus 1.6 times the live load?
That's correct. That's correct. For this load case, always. And remember, if you have self-weight, you have to find weight of the beam as dead load. Yeah, add that to WD 10 times 1.2. Weight of the beam is kind of dead load. Okay, so go to this equation, calculate A, and then F prime AS, and 3.26. We will go to that table. We will go with 2 number 10, 1 number 9. Total AS 3.52 inches. Yeah, perfect. So in this case, you have diameter of this bar 2 number 10. Yeah, diameter of each number 10 is 1.27. Diameter of number 9 is 1.128. Diameter of stirrup number 4, as I mentioned, diameter up to 8 is diameter divided, number divided by 8. So 4 divided by 8 means 0.5. I gave you DS. Yeah, that's the diameter of the stirrup, point S, 0.5. Okay, so I need those. You can see where. So then I calculate beta 1, and then I calculate C. So I calculated A, C, A divided by beta 1. That's your A, your C. Then I'm checking if this rebar that I am going to use can be installed in one layer. That's important. Yeah, always you have to do it in your design. Okay, so as you can remember, the distance between the rebar in the first, actually last class, the distance between the rebar must be the maximum of diameter of the bar or 1 inches. Okay, see which one is greater. If you have combination of the rebar, go with the diameter, the bigger diameter. So here, 1 inch or 1.27, we have to go with 1.27. Yeah, that's based on the code. So the distance, clear distance 1.27. We have 1.27, 1.28, 1.128, 1.27. Yeah, diameter. 1.27 distance, 1.27, 0.5, 0.5, 1.5 inch, 1.5 inch. Yeah, clear cover, as you might remember, to the stirrup should be 1.5. So I will add them together. Required D based on the code should be 1.5 plus 5, 1.5 clear distance plus diameter of this 0.5. Yeah, I will write everything here. Then I have 2 number 10. Look at this, diameter of 2 number 10. Okay, 1.27 diameter. I have 1 number 9, 1.128. I have 2 clear distances equal the maximum of this or 1, that is was maximum, and we have 2 of those. 2 times 1.27. Then I have half an inch diameter of the stirrup plus 1.5, half an inch, 1.5. So yes.
Where do we find the dimensions for the clear cover for each number rebar and the stirrups?
And look at this. Each number rebar and stirrup, that's the last week I gave you, that's the minimum required 1.5 clear distance. Yeah. So that's from the code. You must remember that. You must have that.
But
so
the
1.5 always.
The 1.27 and 1.28 though, or
these 2.
Yes, where did those come from?
From the table for number 9. Number 9, go to that table, you can find the diameter. Yeah, look at this. This is the table that I put that here. Number 9, diameter, 1.128. Number 10, diameter, 1.27. Clear?
Okay. I thought it was the clear cover for those.
No. Those are the diameter of our. Look at this. DD. I put that, look at this, I show that these are for these numbers. Yeah. So we add them all together, you will get 10.2 and is greater than 10. So 1 layer is not acceptable. Is that clear? Always you have to check to see if you can't just put as many as rebar that you want and you say, okay, that's okay. No, we have to check it. And it's not good, so we have to go with 2 layers. Yeah, in this case, with 2 layers, you can have, based on all these dimensions here, I wrote that how to calculate D, how to calculate DT. So you have all these stuff here, D and DT. This is the calculations here. Okay, so I will go with 2 system, and in this case, again with number 4 and with 2, it should be for sure okay. You don't need to check that anymore because it's very close. If you remove 1 bar, you will be okay and you have enough distance. So in this case, we have to actually based on this A that we calculated, yeah, because we calculate, we have to recalculate everything. We change a lot. So in this case, we have different D. We have to use different D. You have to go to this equation again with the same mu, but different D. Everything is the same except D. D was, where did I write that D for you guys? Let me see if it was in the example. Yeah. It was, yeah, you can see that's correct. D H minus 2.75. Thank you. Yes, it's here. So you have this D, yeah, with that 17.25. But in this case, we changed that D to 16 inches. So we have to redo everything. based on the new D, yeah, we will go to this equation. You can calculate 6.5 AS, and then rho is, you can see rho is greater than rho max, yeah, so compression rebar is needed. We check again everything. So, and right now we have this stuff that we want. And in order to find the moment capacity based on this compression bar, we will go with AS with the maximum, yeah. What's the AS maximum? It's rho max times DD, yeah. That's the maximum tension bar that we can put. And that's the rho max, 0.026 times 10 times, this is the maximum tension bar balance with compression concrete, yeah. If you use maximum tension bar, that is that can work with the compression bar, so in that case we use AS max based on the rho max. So based on this rho max, we are using this equation based on A. Find this A. So in this case, A is AS, we calculated here, yeah, that AS, and this is your, no, sorry about that, that's AS. You are using this AS here, 3.3, FY 60, F prime C, and B10, so we calculate this A, because we know AS in this case. That C is, you can calculate based on beta 1, and then calculate phi. The phi is 0.862. We didn't assume anything, but we need that. So then find MN2. MN2 is based on the concrete and the rebar. Tension rebar we calculated for MN2. This is a good actually example to see when you want to design something that you know the scale. At first, I will go with the maximum rebar for tension bar. Then the rest of the load will go to the compression, and you can find the compression bar. So this is a tension bar. That tension bar is this part. Look at this. Let me show this one more time. Look at this. The bar. Yeah. MN2 will come from tension bar, and this tension bar we consider that as a rho max for tension bar only. Okay, so with that tension bar only, we calculate that MN2 0.85 prime C AB. We calculate AB. You find this is inch kip. So F prime C is KSI. So at the end you will get inch and kip. Yeah, and we know that the moment nominal moment capacity is Mn1 plus Mn2. Okay, we calculate Mn2, and then you can and we know the total moment required 25-30 pound kip, inch kip. This is the required. So that's our MU for this side. So I will write this times phi. Phi means MU capacity is phi Mn equal phi Mn1 based on the compression bar, phi Mn2 based on the tension bar. Okay, so we calculated phi Mn2. We know Mu based on the loading. Yeah, we want to at least equal to required. So that's the provided, at least equal to required. So required here, phi Mn1 plus phi Mn2 means this one times phi. Yeah, 0.862, that's our phi. So from here you can find phi Mn1. So we need this moment capacity coming from the compression part, because phi Mn1 is for compression part. Yeah, that's it. How can I find Mn? This one divided by phi. You can find Mn1. So right now we have the Mn1, and we want to calculate the rest of that. You have to come up with the rebar. Yes, what's the question?
Where did we solve for Mn1?
Look at this. Mn1, this is the equation. Mn is equal Mn1 plus Mn2. Yeah. Then because always I want to use that load, ultimate load from loading moment from loading, so times phi, both sides. So you will get mu, yeah? Then this is your mu, this is your mn2, this is your phi mn1. Then from here, that's a required phi mn1. Then required mn1, okay? Then go after this one. Comparison rebar stress. You can calculate this based on everything that you have, yeah? Then F prime C, F prime S, that's your stress in compression bar. You can see it's less than Fi, so you can assume, you can accept this. It's less than Fi. If it was more than Fi, you should consider F prime S is equal to Fi. But here is less, it's good. Just that's the comparison. Then how can I find Mn1? That's the equation. A prime S. F prime S, D minus D prime. Where did I get this equation? Let's back one more time in this slide. You can see Mn1, Fa prime S, D minus D prime. That's the same equation. Okay. Let's go back, and with that equation, I want to find A prime S because I know Mn1. We calculated on the last slide. So I rewrite this based on A prime S. Yeah. Then put all the numbers in this, plug in the numbers, and you can find 0.462 square inches. But most of the time, it's too small rebar. If it's too small rebar, it's better not to use that. We went with 2 number 6 is much bigger than this. This is experience. Why we are not using that small? Because those are very teeny tiny rebar. If I use those too small, during the construction, you are walking over these beams. You can bend them, and you will lose the actually distance between, you need this D between actually distance between compression and tension rebar. If you make it smaller, the capacity will reduce, and because of that, with our experience, even we don't need this big, but we will go with 2 number 6 to make sure if they walk over those rebar on top, they cannot bend them easily. Yeah, that's the reason why we pick bigger than this, too much bigger. But for the bottom rebar, we don't care. It should be close. But here, bigger. Then tension rebar calculation. How can we calculate tension? AS is equal AS max. We assume that side. Yeah, look at this. We assume for AS is equal AS max. Yeah, 3.3. Then plus this rebar. Okay, so plus A prime S. F prime S divided by F5, so it should be 3.3 from AS max plus A prime S. We calculated here, yeah. Actually, we calculated based on this. We used that number, but you don't need to go with this because it's too big. We don't need that. We need this one. Just remember, in this equation, whatever you need, don't go with that. Go with this because this we don't need this big. We did that based on experience. So in this equation, go with what you need based on the calculation. So A prime is 4.62 times F. You can do this one. So this is the rebar that we need. We will go with 4 number 9, total AS 4 square inches. Then I have to find check if it's not less than rho bar max. So I calculate rho bar. Rho is AS, what we use, BWD, that's rectangular. Rho prime, do the same with this number, what we used, yeah, in this case, because we used bigger. So, and this one is good too. Look at this. If I use bigger rho prime will increase rho bar max. That's one of the solution. If your rho is greater than rho bar max, you can increase the compression bar. Look at this. If you increase the compression bar, it will increase rho bar max. So if its rho is greater than rho bar max, go and increase this bar. So it's one of your solution. See? Just, you can see here. So we have this rho prime, then put in this equation. Yeah, that's the equation. Find A, and based on the A, you can find C, and then based on the C, calculate phi. And your calculation will give you a smaller number than 0.9. Stay with this. Do not change that because it's between the limit. Yeah, so that's your fee. Then go inside this equation, check this actually equation. Yeah, and I gave this one if for there is no need for this one because we calculated that. Yeah, forget about this line. I have to remove that from here. Just this one. Don't work on this one. Row bar max. We are working on this row bar max. Row bar max is row max plus this one. Yeah. So we have row max from the tension bar only plus row prime, this number, times F prime S 53 something that we calculated in this slide. Yeah. What was the, look at this, 55.3. Yeah. And then time, and you can get this number. Yeah. This is your maximum actually row bar, and this one is greater than row. Yeah, this row 0.025. So we are okay. If it was less, one of the solution, go with the bigger size of the compression bar. Instead of 2.6, go with 2.8. Yeah, so you can increase it, so it should be okay. So that's one of your solution. And what's the final equation for moment capacity with compression bar, tension bar with the compression concrete, tension bar with the compression rebar. Yeah, that's Mn1, Mn2, Mn1, Mn2. Add them together and C times that, that's your 2803 is greater than what we want. Yeah, 2530. So it should be okay. That's the solution. You can see this part is not as easy as a tension one, and you have to do harder work on this one. It's not that easy. And like before, please, working on the examples, try to solve them by yourself. Then go after the homework. Yeah. Otherwise, you will get more problem on the homework, and you see why I can't solve them. Maybe you cannot solve the examples as well. Just try those first, and then go after the homework. I had some more for this, but we can't cover that. So I think next week I will go after these 2 pages first, and then I will continue other part. So I think that's good enough for today. Thank you for actually being in this class for this subject. And yes, what's your question?
Can you go back to the last example on the last page, the last slide?
Sure. Here.
Yeah, so you went pretty quick, and you said we should change rho or rho prime when we get to the rho max equation.
Yeah, look at this. We did that. We find the maximum rebar that we used. Yeah, we used 4 number 9. Is that correct? So it means that 4 square inches. And we use 4 square inches for rho. For rho prime, do not use this number. Use whatever, for this rho prime, yes. For sorry about that. For this rho prime, yes. For that AS, do not use that A prime as that we used. Use whatever we calculated for AS, not what we used. So for this rho prime, what we used, so use this here, yeah, and then put this in this equation, and then you can see instead of rho prime and see you are good or not.
Okay, thank you.
Did I give you the answer?
Yeah.
Okay. So I can see more students, they have question. Any more question?
I had a quick question, Professor. You said we know how to, because you know where it says use 2 number 6 and use 4 number 9. You said we would know how to use that with experience, or like how do we choose that again?
You are talking about 4 number 9 or these numbers?
Yeah. Like how did you know to choose that?
Look at this. First of all, you want to get close to 3.76. Yeah. So that's the first think that you have to reach to this. Is that clear?
Yeah.
Okay. So I will go with a combination of the reward that is close to this number. I know each number 9 is 1 square inch cross section. So 4 of those will give us very close to this. But it needs some experience. Yeah. So you can do it right now. It's not that big experience. Yeah. But you have to do a few times, then you can see that how many and what combination. You might go with 2 number 9, 2 number 8. 2 number 9 at the bottom, 2 number 8 at the top. Then match and see if it's good or not. And at the end, you must be able to, your MU provided greater than required. So maybe you will go with another combination and it's not good enough, then you have to redo this again. Yeah?
And where do we get that in the code book? Is in the ACI code book? The rebar?
Which part?
Like the T number 6 and knowing that's 1 inch squared. You said we get that from the table?
Yeah, the size of this, you're talking about A prime S?
Yeah.
A prime S, I show that. Look at this. That's the table. Number 6, you will get 0.44 square inch for each one. We have 2 means 0.88. Yeah?
Okay. Awesome. Thank you.
Yeah. Okay, very good. Okay, so is there any other question?
You said we could go over homework in lab tomorrow, correct?
You can go over the homework and yes, today's lab or tomorrow. Tomorrow is better because today I have this class, then I have lab and I have to give you a lot of other information, but tomorrow is the best. If you can come tomorrow, for sure after the lab hours, you have the whole lab to ask your questions.
Can we go to both labs? Or
Yes.
either or, I mean?
Wednesday is better because look at it right now, it's almost 2 hours I'm talking. Then for the lab, I am going to talk about at least 1 or more than 1 hour. So at the end, I don't know how many more questions I can answer. But tomorrow, because I have just lab, so you have the whole 2 hours for your questions. I prefer to come on tomorrow, but if you have questions that can help you today, stay, and today I will answer you.
What time is the lab tomorrow?
Tomorrow should be 5 to 7:45.
Thank you.
Yeah, please be on time, or at least don't come that late, because if you are assigned to today, not tomorrow. For tomorrow, if you want to come for asking question, do not come that late, because if nobody is there to have question, then I'm not staying. Otherwise, if I know if you are coming at what time. For actually question is, do you have a preferred office time we can schedule for like once a week? So actually, what about the Wednesday after about maybe 6? Is that good? Between 5:30 to 6. You can come and all the way to the 7:45. So every Wednesday from 5:30 to 7:45.
And that won't
Please, yes.
that won't interrupt with the lab that Wednesday class is enrolled in?
No. Look at this, because lab, I'm going to give them some information like today. I'm giving you some information. Then after the information, that will not last that long. The rest of the hour is for answering your questions.
Okay.
Yeah. So, do you want to stay for the lab?
I have class just during the Wednesday lab, so.
So if you have no question, you can go. Yeah, if you have question, please stay and ask.
Professor, I have a question about the lab. Is everyone required to attend the lab?
Sure.
Alright, so everyone is coming tomorrow for the Wednesday lab?
So you are assigned to Wednesday or Tuesdays?
I'm assigned for Wednesday.
For Wednesday, and I send you email, 4 emails to give me the answer. Did you answer me?
Yes.
Okay, very good, thank you. So it's sure, for the lab, you must be in the class, yes.
Alright.
Okay.